I mean, this is Darren. Darren, I mean, I don't really know, but I think that they're going to want you to know both. And I know a lot of times I think people want, you need to start off with simpler models, or when a simpler model can solve a problem, it's easier to implement, maintain. There's also explainability reasons at this point as well. So if you went into an interview and you had little or no experience with traditional methods, I think you might be, at a disadvantage. Just my guess.
I don't know for sure, but I kind of agree with you, because as I was telling Charles before, I think that a lot of people out there who are doing NLP in these companies are pretty much, they've been doing NLP for a long time, so they're probably very familiar with the classical methods and maybe not so familiar with the deep learning methods. And so when they interview new people, they're gonna go with what they know. They're gonna ask them questions about classical NLP as well as deep learning NLP.
So I'd also like to add something. So I've been working at a startup in India, which is doing NLP in the field of misinformation. And yeah, for the past 1 year, we've been looking a lot at deep learning methods for NLP. Also looking at traditional methods, because the thing is, more than which method to use, one major factor is how easy can it be deployed and how fast is it in inference. Because if you're deploying it as an API, there's no good if it takes a long time for inference as well. So that's also one of the factors. And a lot of times, let's say not extremely traditional methods, but say something like word to vec, and you add something like a combination of word to vec plus word overlap. It's a very strong baseline for comparing, say, sentences or getting sentence similarity. And a lot of times that beats, having a really expensive model for like a deep learning model for computing similarity between two sentences. So it depends on the problem, also depends on exactly what the main goal is. So we're pretty open with that, and we use a lot of that. Traditional methods, but let's say we won't go beyond before word to vec, you know. That's the limit that we're going for.
That's really interesting. I mean, so you're saying that when you look at the trade-off between how fancy the model is and how easily you can deploy it, and how fast the inference can be, you're saying that for some purposes, in your case, looking at similarity between two sentences, because you're looking at applying deep learning to identifying misinformation, you're saying that sometimes the classical methods can beat the deep learning methods in ease of deployment and fast inference. Is that right?
Right. Yeah. So something like that. So let's look at sentiment analysis, right? If you look at what really good models for sentiment analysis are, like you can get like one of these new models, BERT and ExcelNet. They're good, but let's see, if you compare it to say even ULM Fit. ULM Fit, BERT is say a little more sophisticated than ULM Fit because it uses transformers, but a ULM Fit model is a little much more easier to deploy, is lighter, and it also gives you the same accuracy. And even a naive Bayes model or a CNN model gives you pretty good accuracy. It's like for sentiment analysis. So not a lot of times deploying a BERT or ExcelNet model, which is like a 1 GB model, compared to these models which are much lighter, is much easier and also much scalable, because you also have to look at cost of the server. You can't always be deploying it on really expensive servers, or ease of training, because say ULM Fit you can easily retrain. Same with the CNN models, you can easily retrain. The BERT models, they are not as easy to retrain as the ULM Fit model. So you also have to look at that as well.
That's a really interesting perspective that only could be given by someone who's been working in the field. Thank you for that. One thing you said that I wasn't sure of is you talked about CNN models, and I don't think we've talked about that in this class, and I'm not familiar with CNN models applied to classifiers. Could you talk a little bit more about that?
Yeah, so CNN models are actually pretty useful and pretty understated. You know, it's like they're actually very good for classifiers. Uh, so what CNN models usually do is you can think of all the, if you pass words of a CNN as, let's, you've got a sentence, and instead of a sentence you pass the filters of a CNN, you can think of them as taking n grams, right? So if you have a one filter CNN, which will probably look at one word at a time, then you can have a filter, a 2x2 kernel, which will probably take two words at a time. And what it does is it generates, let's say, an average pooling layer, and that average pooling layer is then passed through a linear classifier to get you the final predictions, and that's actually very accurate. In fact, CNNs are also used in Elmo, the Elmo architecture, for generating word embedding, context-based word embedding. So CNN is like the first layer before the two BILSTM layers. So CNNs are actually very useful for generating word embeddings, or taking the average of the word embeddings in through the kernels are basically used in such a way that you can take more, let's say, a deep learning method of taking, say, some combination of the word embeddings to pass it through a feed forward layer for classification.
Hmm. So it's like a one-dimensional CNN?
Yeah, mostly, yeah, 1D CNN, and the kernel sizes are basically, let's say, they basically take an n-gram combination, and then they take the average pooling, or you can try other pooling as well, max pooling as well. So it's
So you can
basically
do
building on those theories.
Sorry, so you could use kernels, you could have different kernels for 1 grams, 2 grams, 3 grams, and you can do up to as many n grams as you want?
Yeah, you can, yeah, it's there. So let's say, so the thing is, it depends on the problem and it depends on your experiments as well. CNNs have been known to give you good results. So it's definitely something, if it's a classification task, it's something that can be tried on, because it doesn't need a GPU system to train on. A 1D CNN can be trained on a CPU system as well. So that's like a really big advantage.
So that makes them easier to deploy and, well, easier to train at least. Since they
Yeah,
don't
easier to train, and easier, more easier to interpret as well. Using hooks, you can get a good interpretation as well.
I see. Thank you so much for that. Any other questions? I think there's one on the chat that I see. Let's see. Oh, someone says, is it possible to construct a translator for old native language, and what would I need to and from that native language? I think we'll see in this lesson that if you start with some kind of like a Wikipedia database for that language, then Jeremy has a general method that can translate any language given a Wikipedia database for that language. So if there is, like, if suppose you're talking about a Native American Indian language or something, if somebody has constructed a Wikipedia database for that language, you could start with that and then do the translation into English. So let's see. Somebody said, could you repeat what is the tool used for interpretation? I'm not sure what you mean by that. Mani-san, could you rephrase or ask it again?
I think, I don't know who, he mentioned about CNN is very, that can be trained in CNN, in the CPU,
Oh, yeah.
and it's easy to interpret. That's what I was wondering, like what was the tool used for interpretation, or just the
No,
I'll hand that over to Abhinav.
yes, actually, Yes, actually, I was referring to hooks, something which Jeremy taught in deep learning from the foundation. So it's not something that I've done extensively as well, but I know that, using hooks, you can maybe find out what the
Hooks. Okay.
gradients are. Yeah,
Okay. Okay.
yeah.
Okay, great. Any other
Actually,
questions?
I have a quick follow-up questions for Abhinav. So you mentioned that you look at both like classical word-to-vec embedding and UML fit embedding or UML fit model. So I'm actually trying to use both. And what I don't know yet, and I was wondering if you would know like the answer. So I need to do a transfer learning, take generic model and move it into my domain space.
Okay.
Like, do you know? Can you tell like which one would like if you like theoretically UML fit should perform better if we give it enough documents. But let's say we have limited amount of documents. Do you have a feeling that one would do better than the other?
From what my experience is, ULM Fit actually does really well for even with a limited set of documents. Unless, of course, you're trying to train it completely from scratch, then you might need. But you can probably, if it's in English, then maybe you can train it on top of the pre-trained wiki model and see how it works. But like I would have to obviously see the data, and I'm also, learning, and I've been working in NLP for the past year or so. So, I still have a lot to learn. Uh, for what I can say that ULM Fit is easy to train and also doesn't need as many documents, as we probably think. Uh,
Mm-hmm.
and I think if it's in English, and I think you can try the pre-trained wiki model and just fine tune it on with your corpus and just see how the classifier behaves.
Okay. You haven't compared it to, let's say, word-to-vec retraining for like for any
No,
of
so
your tasks.
Word2Vec basically, Word2Vec I generally don't use it for classification. We generally use Word2Vec for finding similar sentences, sentence embeddings, mostly.
Yeah, that's what my problem, my kind of task is. I'm trying to find matches, which is or like mapping or translation, and we use the pre-trained embeddings, and we plan to retrain them in the specific area. So
Okay.
yeah. So, but I kind of
So
I don't have a good feeling in advance like which one would work better.
so yeah, generally in my case, whatever I found is that whatever my data set is, I would always prefer to have an embedding in that space. So whether I'm using ULM Fit or Word2Vec, I would probably just train it on top of my documents, whatever I have. So there's a better relation. You can get a better relation between the words, between two words of your whatever your data set is. So you can, you can train it on ULM Fit and just extract the first layer, which is the embedding layer, and you can even convert it to Word2Vec. I think there are people who've done it for other languages. I think there's one person who did it for Thai to Vec. He pre-trained it on Thai wiki text, and what he did was he just extracted the first layer and he converted them into a sort of a Word2Vec embedding file which he would refer to. I'll just paste the link in the chat. You can probably refer to it for your reference.
Oh, cool. Thank you so much.
So Abhinav, is that the same as just saving, like when Jeremy when he uses the ULM fit technique and he just saves the encoder? Is that the part you're talking about? The word-to-vec
Yeah.
encoder?
So the encoder has multiple things, right? It has an embedding layer. It also has an AWT LSTM layers. So what you can do for if you just want the embedding of the vocab, what you can do is you can just extract the very first layer of the encoder, which is like the encoder is also a list of three things. It will have an embedding layer, and I think it has two AWT LSTM layers. If you do learn.model, the whole thing just comes up. So if you have the notebook loaded over here, you can probably try that. Just do
Yeah.
learn.model. You
Yeah.
see a list of all the embedding, all the full architecture. And if you do learn.model index at 0, then you get the embedding layer. So what you can
Okay.
do is you can just take the words in the embedding layer and you just convert it. So I'll just share the link that would make it a little more clearer.
Okay. Okay. Thank you so much for that. Any other comments or questions before we start? Yeah, I'm just going to wait. Are there any comments or questions before we start?
Maybe a question. Anyone actually like used code search related or in a specific like methods, functions, different languages? Because those are all the things that cannot be like, we cannot leverage Wikipedia for our so wondering if anybody like worked on transfer learning on code related stuff.
Huh. Ah.
I think
I've
Microsoft.
heard people. I've heard. Sorry, go ahead, Yuri.
Oh yeah, I think Microsoft just published a network that was trained on GitHub.
Okay.
So basically, yeah. If you look at news, if I find it, I'll post it. But yeah, it's meant to make it easy to find code.
Okay.
Yeah.
All right. Thank you.
I know that somebody trained just as a joke, they trained a model on Stack Overflow answering questions, and they used the Stack Overflow database and trained a language model to create answers to questions. In other words, instead of predicting the next word, it would predict the next sentence after a question in a Stack Overflow-y kind of way, and so the answers to the questions were just bogus, but it was entertaining for a lot of people.
Mm-hmm.
I think they mentioned that in one of the in one of the Fast AI videos. Yeah. Anyway, okay. So that's a good question. So let's get started. Can everybody see my screen? I'm looking at the. Actually, no, I'm looking at the wrong one. Let me just go to where I want to be, which is the NN-IMD-more. Can everybody see that on my screen? I'm just wondering what you're seeing.
Yeah.
Yeah. I'm sharing the right thing. Okay, thanks. All right, so this one, it seems very similar to the one we went through, the NNMDB, and I didn't bother to look back, but to see what's different. But I think there's at least one trick. But let's just go through this. So here's the, it's applying the IMDb. It's building a classifier, a sentiment classifier on the IMDb, the same way we did before by first building a language model, and then so this is the language model step. And I told you before that because I have a Windows machine, I'm not sure if this is common to other machines. I've never heard anybody that has a Linux machine complaining of this, but I found that this particular line gave me a lot of trouble. It kept failing, so I had to construct this sort of brute force thing that just keeps trying it until it succeeds. And it keeps track of how many. In this case, it was able to do it with just one failure, so that's fine. But it's the problem. There's a stochastic error in either the FastAI library or it's in PyTorch. I'm not sure which is causing the error, but I have. Yeah.
I'm sorry, I have a little bit of a silly question, but how come everything's in a tuple? So data LM. I mean, all you're doing is calling a bunch of stuff in series. There you go, like the dots, right? Data dot.
Yeah.
Dot. So then why do you put the brackets around it to make it the result a tuple? That's like, I see that as a pattern in FastAI, and I don't think I've seen that in other places.
Okay, you mean these brackets?
Yeah, those at the outside, aren't those just making it a tuple? The result?
No,
No,
that's actually making it a single command. So that tells that just tells the, like, if there's a parentheses around it, that says that the line continues until the end of parentheses. So that's all that is. If you would put this all on one line, you could get rid of the parentheses. It's not making it into a tuple.
I've never used that convention Python. It's confusing. Okay.
Yeah, it's a good thing too, because otherwise you'd have to, commands would break if they were too long and so on. So yeah.
Okay.
Okay, so that's that. I don't know if anybody has ever run into this problem. If they're using a Linux machine, have you ever had a problem with this line?
Looks like a Windows only thing.
Yeah, could be. So that's what it is. All right, so here's what happens. We save the data bunch. We're creating a data bunch with this. That's all it's doing. We save it, we load it, we create a language model based on this, and we put it to mixed precision. That's what this thing is doing. And to do that, you have to have an NVIDIA GPU with tensor cores. My machine has that, but if you're on Colab, I'm not sure if they have, if you're using a certain kind of machine, I think he said a P3, I think Jeremy said a P3, you can do that, get the mixed precision. All right. Then we train for a cycle.
Yeah. Joseph, this learning rate, when you are setting the learning rate, and then like the second line of code, right? LR into batch size by 48. In the
I'm not sure. Yeah.
Yeah, why are we doing that rather than actually like setting directly?
That is a really good question. I think that Jeremy must have found, this is something from Jeremy. It's a heuristic. That is a rule of thumb that Jeremy found. So I don't really know the reason for that. But they try, at FastAI, they try all these experiments to make things run most efficiently and fastest and so on. And I guess they found that setting the learning rate to 1e minus 2 over this thing, or in other words, setting the learning rate to 1e minus 2 times batch size over 48 seems to work for them. So that's a good question that I don't know the answer to.
Okay.
Okay, so he runs one cycle, then he unfreezes, which means, okay, so this is training with all the pre-trained weights that we got from the AWD LSTM model. There's this drop multiplier, which we could talk about a little later. Anyway, train with the pre-trained weights, then unfreeze. That means back up. I mean, let it fit all the weights, and that takes a long time. I had a question about why. When I first ran this, my time was the same as Jeremy's time. Roughly, it's maybe a little bit faster. But then when I ran it for 10 cycles, I found that things slowed down quite a bit after a while, and I'm not sure why that is. Maybe that's just normal. But anyway, this took a long time. And Jeremy says, turn it on and leave it overnight. So you do that, you save it because it took a long time. And then here's the part where they do the save encoder. I'm going to do what Abhinav said. Let's look at. Let's look at that learn underscore LM. And then he said model. Let's look at that. Oops. Because I have to load it. I haven't run this thing yet. I mean, I've run it, but I haven't, but it's not live here. I've just brought it up. So I have to let it load the model. So I have to do this load. I have to load the model that I just saved. So let's see now. Oh, that's not what I want. I want it here. Let's see now. Learn lm dot load.
Joseph, you may want to define the learner.
Oh yeah, that's right. That's right. That's right. I have to do that first. Define the learner. Learner data lm. Learn lm dot fit one cycle.
The language model learner.
Yeah, I have. So to do that, I probably have to let it fit one cycle or something, right? Because that's the place where it's defined. Learn LM. That's the first place that it's mentioned. Data LM.
No, it's if you go down below, there is a one line you miss. Go slow. Hey, where you have.
Did I miss it?
Yeah. So line number 8, 9.
Oh yes, this is it.
Yeah.
Yes, thank you. This is it. Why did it? Oh, data LM. So I have to do that. Then I can do it. Thank you. So now I've got the learner defined, and now I can do the learn lm.load. Oops, now it didn't like that.
Because
Runtime error. Is it loaded? Escaped it. Missing keys. Huh, that's weird. I did save it.
No, you're loading the encoder rather than the, that's why.
Ah, yes, okay, so I can do this. Thank you. That's what I needed to do. Oh, now it didn't like that either. Get out of memory. Okay. Let's see. Okay, so I think I've been playing around with some of these. I don't know why I'm out of memory. But anyway, so I can't do that. So I'll just keep going. Yeah, I mean, if I were to start fresh and reboot my machine and all that, does anyone know the quickest way to get around an out of memory error? I mean, I have all these other notebooks open, and they might be taking up a lot of memory. So I suppose I could back out of them and
restart the kernel. Restart each kernel.
Oh, just restart. Maybe I'll just restart this kernel. Let's see. Okay, let's try that. Restart. I think it's done. I need that. I need that. I need learn. Oh, I need this. I need that. That's done. Okay, so now I can load that. Let's see if it'll do the same thing. Okay, so it did it. Okay, so now we can do what Abhinav suggested, is to look at what's in the model. And so it gives us, the first thing is there's an encoder here, right? And then it has RNN. I don't know what this encoder underscore DP is. Oh, dropout. Then it has RNN. And so then I think then Abhinav suggested we can look at the elements. So I can do something like do this, the first piece of it. Oh, that's all there is. Wait, that's the whole thing. Oh no, it seems to include everything but this piece here, the linear decoder. Yeah, so I think this is what you were saying, right, Abhinav? The first piece, the first element. So learn lm.model, we could probably see that it has that it has a length of 2 or something. Yeah, and then if we look at the first piece, has the encoder in it. And the second piece has the decoder. Like that. Linear decoder. I think this is what Jeremy was saying in the lecture when he talks about how you only need to save the encoder when you're building a classifier, because the linear decoder part of the language model is the part that predicts the next word. Okay, so so he's built the language model, and this is what we get out of it. And then the next thing he says, okay, now we're going to use the language model to build a movie review classifier. So now we get the we get the data and put it into a data bunch, but this time it's a little different. It's not the same command. This is the internal command. I built this wrapper to make it run in my machine on my Windows machine, but this is really the command that it's executing. And you can see it's slightly different than the one above, building a data bunch for the language model, because now we have to use the, we label it with the classes. Remember, for the language model, we didn't need labels. Okay, so so there's our data bunch that we built. Then we load it, and let's see, I think this part, we can pick it up. And the rest of it is much faster. But so the next thing you do is you, let's see, why is this? This is probably, oh, I was playing here. I wanted to, I think Jeremy said something about looking at this during the lecture, so I thought I'd look at it. Nope. Model data. Maybe we'll just look at the, maybe it's just this thing. Learn C. Let me just, if you bear with me for a sec, I'm going to let it run this. This should be, oh, it's done. Okay, so now I can do learn C, which means the classifier. I should be able to do this _model meta. I remember in the lecture, Jeremy said something about this. It doesn't have that. Okay, well, never mind. That was just something I'm going to try. Okay, so the next thing, okay, we've got the first thing it does is it freezes the weights that it got from AWD LSTM, and then it trains one cycle, and you already got 92.6, a score of 92.6% for your classifier. Then you save that, and you, I guess we can, anyway, you load that. You then unfreeze to -2, and I think that what that means is unfreezing one layer, unfreezing just the last layer. Then you train again, and you get up to 94. Then you unfreeze to, freeze to -3, meaning everything but the last two layers, and train, and then you get up to 94.4. And then finally, you unfreeze all the weights and train it again. And I think I got an out of memory error here, but let me try that again. I think it'll work if I make the smaller, if I use a smaller batch. I know it'll work if I use a smaller batch size. I tried, let's see what batch size is right now. Yes. On my machine, 48 didn't work. So I had to back off to 36, and then it worked. Anyway, so it does work, and you ended up with something like 94.8% at the end of this. I'll run this while I won't run it right now. Anyway, so that was the end of that. We got up to 94.8%. Then Jeremy introduced some interesting techniques. I thought that this NN Vietnamese and NN Turkish was going to be just a review of what we did before, but Jeremy actually introduces some interesting things in here, so we can look. I have not been able to get this thing running despite spending a lot of time on it so far. And the reason I think, again, is that I'm in a Windows machine, and some of this code that he's written is only working for is only working out of the box for Linux. So I'm confident that I will get it working, but so far I haven't. Anyway, he points to this file that he has called NLP utils, which we might look at. Let's see, NLP utils. It's a Python. It's a .py file. NLP, there it is. Open that thing up. And you can sort of see what it is. It has two, he defines two functions here. And there's a lot in here. So the first thing he does is he uses this thing called wiki extractor. So when you download the database, you get it in an XML, in the form of an XML file. If you download it directly from Wikipedia, you get it in an XML file. That's the first thing. And I had some trouble with that, which I'll get to in a minute. But anyway, once you have downloaded from the wiki website, and get this XML file for a language that you're interested in, the next thing you have to do is you have to extract it in a convenient form for language modeling. And that's what this wiki extractor does. So he's got this little routine that actually, under the hood, it actually installs wiki extractor on your machine if you don't have it. And then he uses wiki extractor to extract this thing into a text file that's suitable for building, for the starting point for building a language model. And that's the part that I haven't quite got working yet. Okay, so that's that file. Let me show you where this all happened. Let's see, download. So here's where he imports that stuff. The split from NLP utils. NLP utils.py is sitting in the directory, is sitting in the same directory, so it knows where to get it from. You import these two functions, split wiki and get wiki, which we just looked at. All right. So this is actually supposed to download and extract. So I found I couldn't get it to work. So I ended up, but it gave me an error message, and it gave some instructions, which were pretty helpful. So from those instructions, I followed these. Well, I had to actually figure this out myself here. In order to install, to actually get that file and break it up, I had to install this thing called Chocolatey, which I did. And I didn't have wget. Okay, wget is this Unix program that gets files directly from HTTP, from the web. I didn't have that in my Windows machine, so I had to install it. I had to use Chocolatey to do that. I installed it, and that's how I did it. And I also needed, for later use to extract things, I needed this extractor called 7-zip, which works. I think it also has a, it's distributed on Windows, Apple, and Linux. But the reason is that when you run wget on the wiki website where you can get these languages, they're in the form of .bnz files, which are bn2 files, sorry, which are zipped. And in order to extract it, I needed to get 7-zip. Anyway, so then I was able to run this command. This is the place where you get the file, the Vietnamese wiki. It's called vwiki-latest-pages-articles.xml.bz2. So you have this zip file, and then you have to extract it, and that's what I did. Okay, so then I tried to extract a piece of the NLP utils to do this by hand, but that didn't work. Well, it did work. So I was able to download the file and so on, and then I got it. But then this is, let's see, this is the part where I was trying to use the wiki extractor command to extract that file on my machine, and I did not succeed with that yet. So I'll have to continue with this, not having succeeded running it yet. So I'm just going to go with what Jeremy's done so far. So he was talking about, he had first investigated some using Chinese language, but he ended up using selecting the Vietnamese language because he showed that it was pretty dense in terms of how much had been done creating the wiki, and it had a lot of articles in it. So he thought this was a good thing to try. So the first thing you do is you do it the same way as we did before. You extract things into a data bunch. You load it, then you create a language model learner, again, initializing with the AWD LSTM pre-trained weights. Everything goes the same way. You just, you unfreeze all the weights, you train the model, you save it, and then you can do Vietnamese sentiment analysis. And for that, you don't have the IMDb database. He found some other, he found another database. I'll just open that over here. It's AIVIVN. There's this competition that that they had for Vietnamese sentiment classification. I think it's movie reviews. And so he just loaded this as the model, as the as the data set that we want to do classification. There's a web page that discusses this competition, but it's all in Vietnamese, so I can't read it. I'm not sure if it has an English version, but anyway, Jeremy gave this as the website. The score is computed a little differently. It's computed in an F1 score, which is an average, which is some kind of an average of precision and recall. And since we don't have that built into FastAI, I think he built a function later on that does that for us. Okay, so he loaded the test.csv, which is the set of comments, I guess, that are to be classified. And he loaded the train data set as well, and then he concatenated them both. So here's the test and the train, and remember these have labels, plus or minus. But when you're building the language model, you don't need labels. So he just concatenated those together. This is a little trick. It gives you twice as much data, maybe twice as much. Then you create the language model data bunch like we did before. You then create the language model and train it, save it, and then you can build the classifier just like we did before. It's exactly the same technique that we went through with the English model. And then here's that F1 function that he created to do the F1 score. And then he just passes it to here to the learner. He passes the metric, the F1 score, as the accuracy metric instead of using the default, because he wants to get scores that are compatible with the scores that will be gotten by the competitors in this competition. So he then trains the classifier a little bit more. Let's see. What does he do here? Okay, this is with these first trainings are with the weights frozen to where starting with the AWD LSTM model. Then he unfreezes one of the layers, unfreezes two of the layers, unfreezes all, and by the end he's got like an 89% score. And the competition, he says, the top three scores are 90, 89, and 89. So he's already at the top. He's already competitive with the top scores from people in this competition. But then he says, okay, the winner used an ensemble of 4 models. And I guess this refers to that CNN model that Abhinav was talking about before. Anyway, so he says, okay, well, let's see if we can do something with ensembling. So he then goes on to create a backward model using, he has a separate notebook to do that. And it's so trivial. All he does is he has this function in his data bunch, the place that creates the data bunch. He has this switch here that says backwards equals true. That's all you got to do, and then it loads all the reviews in backwards with the word order reversed, in other words, and then he trains that. And remember that Yeah, so he's predicting, given a bunch of words in a sentence, now you're predicting the words that come before it. So he trains this thing all the same way, saves it. It's a backwards classifier right here. That's this whole notebook, Vietnamese BWD, which you have to run before and save this thing so that you can access it in this NN Vietnamese. Then he creates the ensemble of the forwards and backwards model. So I put a note in here. First, create the backwards model by running the NN Vietnamese BWD notebook that we just looked at. Then he creates a learner from the forwards model, creates a learner from the, and then he loads the learner from the backwards. So he loads the learner that we've already created using the forward model, loads the learner that we already created using the backwards model, and then averages of them together. So you have predictions and prediction. Okay, so this is the predictions out of the forwards model, and then you can get you can do the same thing with the backwards model. Then you average the predictions. That's ensembling. That's the ensembling step. I should make a note about that. That's all ensembling is combining, averaging together a number of different models. And then he runs it again, and this time he gets an accuracy of 90%. So he's slightly improved over the 89% before. And so he's definitely competitive with the top scorers in the competition, which we saw was 90, 89, and 89 somewhere. Let's see, somewhere in here. Somewhere in here he mentioned what the top scores were. I think, anyway, there it is, 90, 89, 89. So he's definitely in the top, definitely near the top score there. So that was really interesting. He did basically blindly, he just blindly applied the same techniques that he did to make the IMDb classifier to the Vietnamese language, knowing nothing about it, and got a top score. That's just, to me, that's really impressive. He doesn't have any knowledge of Vietnamese. He did do this one thing. He noticed that, I think this is what he did for, in general, he noticed that Wikipedia articles that are very short tend to be what they call stubs, articles that are incomplete, and they're mostly boilerplate. And then he noticed that the Wikipedia articles have like a bimodal distribution of length, that there's a peak near 1,000 words, and then there's another peak near 3,000 words. And so he figured that articles fewer than 1,800 words could be excluded because they are more likely to be stubs. And so in his, in that NLP utils, we can see the command, I'll go back to here. He says, this is the actual command that that uses the wiki extractor to extract the articles into a form that we can use them with. He says min text length equals 1800. That's where he does that step. He eliminates articles that are shorter than 1,800 words. Okay. Okay, so that's the Vietnamese. Then he goes on to do something else. He says, okay, let's try something. Let's try something else we don't know about. And he tries Turkish. He tries Turkish EOL-MFIT. So again, he builds the language model. And here he used some domain knowledge. He does it in a slightly different way. Let's see. This is the part that I haven't been able to do yet, so I'm going to skip over this. But he notes that Turkish is an agglutinative language, which means that you can add all kinds of word endings to change the meaning of a word. So here's one word that means fear, and then here's all kinds of endings that you can put on it to change its meaning slightly. And he actually had a Turkish speaker in the class. And Jeremy asked him, well, how far down do people go? Do people actually make words that are this long? And the guy in the class said, probably down to about here. This is, you know, so they would add endings that this is a comfortable length for Turks to speak, but they wouldn't necessarily go much longer. But because of that, he says, okay, here's where the domain knowledge comes into play. If you have, if you know something about, and he just learned this himself by just looking into Turkish a little bit. He doesn't know Turkish. To handle this, he used something called sentence piece that's accessible from FastAI, and that's this. He built a processor using this SP processor, which is using this thing, I think it's created by Facebook, called sentence piece. And what sentence piece allows you to do is it allows you to extract subwords, break the words up into smaller pieces, so that something like, you know, something like this wouldn't be considered a word. It would be broken up into its parts. And he found that that makes it much better to translate to model Turkish, to build a classifier with Turkish. So he used sentence piece. This is the line. And I think there's a default in there somewhere in the SP processor that limits the vocabulary to 30,000 words. Okay, so that's what he did. And then here's a batch that you get out of it. And here's what sentence piece does. You can see that it breaks things into smaller pieces. The words are broken into smaller pieces that are, and it shows that they're connected. I think these little underscores show that this is all one word, but it's broken into smaller pieces that the language model is handling. Okay, so then you build your language model same way as before, and here's that thing that someone asked us. This is a rule of thumb that Jeremy's found out, that you scale the learning rate by batch size. I guess the larger the batch size, the smaller the learning rate has to be, or it can be, something like that. Train it the same way we've done before. And here he converts the learner back to FP32, back to full precision. Then he found this Turkish sentiment classifying competition and this website somewhere. And so he downloaded the data set and used it for this. It's a Turkish movie classifying competition, and it has movies that are classified as positive and negative. So let's see. Oh, and then the other trick. So Jeremy's he kept running into little bottlenecks, and then he solved the problems, and then he told us about what he found out. The files that he downloaded from this competition were originally uncoded, or he tried to read them in with the UTF-8 encoding, which is what most people use in English and European languages. But he found that these files were not encoded in UTF-8. So then he went online and found out that Turkish language encoding is often done with this ISO-8859-9 standard. So he found that he was able to read the files using that. And so he solved that problem. And here are the reviews, the Turkish movie reviews, or the positive ones. And then the negative ones. These are negative movie reviews. So this is the label, pause 1 for positive reviews, pause 0 for negative reviews. He concatenated them both together to get the whole training set. And then he was careful to, when he built the language model for the classifier, he was careful to use the same sentence piece processor. So you get the exact same, in other words, so you treat it the same way. Then he did the classifier, and I guess this is the language model first. Yeah, language model. So this is the same two steps. You build the language model learner, you unfreeze it, you train it again, save it, then you build the classifier. Remember, and then again, for the reason we could concatenate both of these, where is it? Yeah, this line here. The reason he could concatenate these, remember, is that when you're building a language model, you don't care about the labels. right? So that's why, so this is a trick that he's telling us about that he learned himself, I guess, or maybe he got it from somewhere else. It's a trick that gets you more data when you're building a classifier when you're building a sentiment classifier. Because the first step, building a language model, you get to use all the data because you're not using the plus and minus labels for the language model. So this step, you're combining the train and test data. So this is an explanation of why what's going on here. Okay, use the same sentence piece processor that we used before. Then build the classifier in the same way. Remember, just first freezing it, then unfreezing it layer by layer, and finally training it at the end. And at the end, he ends up with a model of with an accuracy of 91%, which just completely thrashes the best result on that website with this data set. So just without knowing, just applying a very few things that Jeremy learned about Turkish, without knowing the language at all, he built a sentiment classifier that completely beats the best known classifier up till now. Then he goes on to say in the last part, he goes on to show how we can improve that 94.8% result that we saw already for the English, for the IMDb database. And the way he did it was by combining, again, the forward and backward models in English this time. And then at the end, he ended up with, this is exactly the same steps that we already seen. He ended up with 95.4% accuracy, which is a huge improvement over 94.8%. Yeah, so that's pretty much the whole. Well, I found out that the last half hour of the video seems to be in a separate video, number 11, which we'll do that next week. That's where they apply this to another problem. They apply the same technique to another problem. We'll discuss that next week. But anyway, so are there any questions up to here so far?
Joseph, just a comment that the sentence piece infrastructure or whatever the processing that he does is actually what is used to get the BERT transformer results that Google has gotten as well. That's a key component, and it's not just used for agglutinative languages, but also can be used for anything like English. The reason for it is it builds the vocabulary from the available characters and from what it sees to be the most common pieces that occur in the data. So it's a very good way to build up the vocabulary with the most common words that it finds, which is not what we do when we take the spacey approach and so on and so forth. And there's like a full lecture discussion of what sentence piece is in the Stanford NLP course, and I'll post a link to that part.
Oh, that's great. Yeah, so I thought that Spacey had something like this where they did the lemmatizing. Isn't that similar?
Yeah, no, but the difference fundamentally in sentence piece is that you take character by character and then you add characters which will result in building up the most common vocabulary.
Oh, so it's at the character level instead of a word level.
Yeah, and it could be at multiple levels, but at least as used for the BERT transformer case, it's at the character level for English, and it helps build up the most common vocabulary rather than take words as given and then just use the most common ones. So it goes one level down and then builds it up from there to get the results that the BERT transformer from Google, they've obviously gone a lot further, but the original BERT transformer paper uses sentence piece, and that's how it builds it up. So it's not just that that's a processor used for Turkish or other such languages, it's actually used for English as well.
Good point. And I think that Jeremy actually mentions that at the end of the, well, at least at the end of the part of the video. I said we should just look at the first hour and a half, I think, of that video. And towards the end there, when Jeremy talks about this thing, this is the example that's in the FastAI library. So that's what I'm looking at now. Jeremy points out at the end of this discussion, he says the same thing that Srinivas just told us. He said that you could even improve more on this result by trying to use sentence piece as the to build the language model. So I don't know if people have taken him up on it. I will bet they have. Somebody's probably done it and gotten even a better result than this. Yeah.
Srinivas, is there a concept of vocabulary in sentence piece?
Yes, in the sense that ultimately it results in building up a certain set of most commonly used words that it builds up from characters.
Okay.
So it stops at some point, and in fact, the stopping number, if I recall correctly, and I could be wrong, is chosen, meaning it's like a hyperparameter that you choose. You tell it, okay, after you've built 30,000 of these things, stop.
So that's built into sentence piece, the 30,000 limit?
Yes, that's the 30,000 you see, because basically it builds up from characters, and you can tell it to keep going until 50,000, and it'll build 50,000 of these pieces.
Yeah.
So your if I actually looked at the vocabulary, when you've done that, would the vocabulary look like just n-gram characters, or would it actually be
Yeah, it would look like n-gram characters.
So you'd have a huge, huge vocabulary. You're basically making the morphology of your language huge, and then you're counting up the common ones and eliminating the rest.
And the huge thing, at least as far as English, is where I've actually seen it applied. Since I don't understand, for example, the Turkish language, I don't know whether it breaks it up to character or it breaks it up to a bigger pieces than characters. But in English, you're limited to 26 characters anyways, right? So it just builds up from there.
I've heard that it's a really good way to capture things like emoticons and emojis and things like that as well. So for social, doing NLP on social stuff, it's really
right,
good.
Because it doesn't care what the underlying stuff is. So instead of 26, you just throw in the emojis into it as well, and it'll build up the emojis, and it'll know after this particular combination of characters, this emoji occurs most frequently. So I'll just throw that in and form a sentence piece from that. That's the beauty
really
of this approach.
Yeah, sorry. Yeah, so if you will post that for us, the link to that lecture on the NLP class, I think that would be interesting to some of us. That'd be great.
I'm curious if anyone actually has used a sentence piece in Kaggle itself, and if there are any.
Well, I think just as we were in, I believe there was a Q&A contest that took place fairly recently, and I would be surprised if somebody didn't end up using sentence piece in response to that, because that's this, like the Squad 2.0 Stanford question answering data set, and the best scores that people have gotten have been BERT based. And if it is BERT based transformer models, you are essentially using sentence piece underlying BERT. If you just use a BERT pre-trained model, essentially what you have done is use sentence piece underlying. So that's the issue, right? After you have trained and you have gotten a language model or a BERT-based model or a ULM fit-based model, you don't really need to go back and build it up. You just use the language model that's already available, which is pre-trained. It's like training ResNet on ImageNet and then using ResNet pre-trained weights. Then you don't need anything that's been done to build up that ResNet weights.
Okay.
So have you, Srinivas or anybody else, have you heard of the Hugging Face tokenizer? It's supposed to be the latest.
Essentially, I haven't played with it myself, but Hugging Face essentially uses a lot of the BERT transformer. I mean, the most recent NLP infrastructure and applies that to get the results. So yeah.
Is it a tokenizer then, or is Hugging Face a tokenizer, or is it a new form of a classifier? I mean, of a.
I haven't looked at it. I just know that they apply a lot of the latest techniques and release the code, and you can use their models much like you can use fast AI models, pre-trained models, or PyTorch models and stuff.
Well, they have a bunch of transformer stuff, but they also, the tokenizer thing's a new thing from them, separate from their transformer.
I see.
Yeah, and that when I looked at that tokenizer briefly, it's definitely a sentence piece. I mean, a word piece. Subword tokenizer. That's what it seems to be most focused on, at least, and a very fast one.
I see. So I think that Fast AI has incorporated that the Hugging Face into their library. I think I saw something from Fast AI where they've got they've built the interfaces to Hugging Face into the language modeling now in Fast AI.
That's good. That makes sense, because I think their specialty is transformers.
Okay.
Also the thing that I was happy about or interested in using, although compute problems limited me, was the fact that sentence piece otherwise was only available on TensorFlow, and I was happy to see that there's a PyTorch version available through Fast AI now.
Nice.
Oh, great. Okay.
Right. So because that's what Jeremy is using here, but all the sentence piece implementations I had seen before were TensorFlow, because that's from Google. So there's no reason they would port it to PyTorch.
Right. Oh, so sentence pieces from Google then?
Yeah, it's from Google authors, at least that much I know.
Okay. And okay, great. All right. Are there any other comments, questions? Because we have some time. So the next.
I got a question. Can you go back and dig into, remember how you actually looked at the network, the architecture, the neural network architecture, and it showed that dictionary and it had classes in it, the pieces. Yeah. Can you actually pull out the embedder and do something with it?
I think that's what
I don't think it's the whole first. Is it that whole first chunk? The
I think
AW,
so.
or is it?
Yeah, I think
who? Yeah. See, I sit there. I think. I mean, I would like to know who mentioned that on the call. Maybe they could guide us through it real quick, because I'd like to pull it out and then like query it or something.
Yeah, that was Abhinav. Is he still here?
He's on the call. Yeah.
He's on. Yeah. Huh. Abhinav, are you there? So I think this is what happens when you do save encoder. Is it saving this part?
No, that's true. But I think you can dig into that object you're getting there, the AWDLSTM, and get the other pieces out, and that might actually get the word. He's talking about you could get the individual heading out of it, and then query by terms and get other related terms out. I think.
I think there is I'll share a post where it actually the author does it for you. It's a spam classification post.
Okay.
Yeah. So if you index the first part, right? You can index more into it. So like if you go learn.model 0th of 0, you can double it.
Okay. I was just going to look into it.
But you're digging into the dictionary, or no, I guess it is the object. Sorry.
Okay, well this is what's available, but Abhinav is saying that we can actually ask for more to dig into this piece here. So let's just ask for We can ask for how long it is for one thing. Oops, it doesn't have a length.
I think he means
Maybe
learn
try it with encoder or something.
zero index and then add another index after that. Yeah.
Yeah, but I thought that in order to do that, you have to have a length. It has to have more than one piece.
Let's see. Wait, I've definitely done this. So let me try to remember how I did it.
Okay.
Maybe try to do something like dot encoder or something, learn.lm model dot encoder, something like that. Because
Okay, yeah, that's what I was looking for here. Let's see what we can, we can see what's in it by doing the DIR.
you see the embedding layer is like just there. You see the embedding layer is just there. If you look at the learn.model,
yeah,
right?
there it is right there. So you can ask for, so when you do a DIR, a directory of, it's showing you all of the things inside that you can, all of the methods and properties that you can access. So, and as Abhinav said, you can get at the encoder. So these are all the other properties and methods that you can get. So if we did this, learn LM of 0 dot encoder.
I think you have to do model.
Oh, what did you say, model?
Learn.model.
Yeah, learn LM.model. Thank you. Yeah. Dot model of 0 dot encoder. We can get something.
Yeah.
And there it is, embedding 60,000, a length of 60,400 components.
Cool. See if we can query it. Is there some sort of where you can put in a word and get like words?
Well, let's see what we can do with it.
Does anyone know what kind of embedding that is?
Sorry, can you repeat?
Does anyone know what kind of embedding that is? Because there's different kinds, right? Is it a word vec?
So it's basically like a word embedding only.
Well, I know. I know that. I just didn't know. I thought there were different flavors of word embeddings.
Yeah, so you can use it like a word-to-vec embedding. You know, it's a lot of people have actually when they're trying to make embeddings for say different languages to use it in a format of word-to-vec. They just convert this. So I just shared a link which I'll just share again, and you can just use that as reference. So this GitHub link that I've shared, this person, he or she, what they've done is they've created a Thai to vec, so they've basically trained a ULM fit model on Thai Wikipedia, and what they've done is they've taken the words and they've converted into embedding, just like how to use it like Jensen's word to vec,
Right. Yeah, I've done Jensen's. That's good. It's interesting that you can do this here too.
So nice. Let's see. So this tells you how to use it. I've done basically what I've done, trying to do what Darren asked for. I'm looking at how do you use this thing, and it's giving me examples. Apparently, I tried to give it a word and get an answer, but maybe I gave it the wrong way. What if I do?
You don't have to give. So it won't take words, but every word in your say vocab, right? If you look at learn.data.vocab.itos, learn LM.
Learn LM.
Yeah, learn LM.
Data.vocab. .itos. That's integer to string.
Yeah, and you take the 0th element, right? So say take the 0th element. I think you have to do learn.lm.
Learn LM, yes, thank you. Yeah. So we could do that.
So this
so that's
will map.
unknown.
So this will map to. So this 0th index will map to the 0th index of the embedding.
Okay, let me try something. Let me try something that actually will be a word. Okay, so that word is less. So you're saying that. So let's see. So you're saying that EE, this encoder, knows about this So if I ask for EE of 360,
Yeah.
or
Should be
maybe
square brackets.
yeah, that's what I thought. Oh, I didn't like that either. Embedding object is not subscriptable, huh?
Interesting. Interesting. Wait, let me see how it could be done.
Maybe
It
it's a
definitely can be
maybe,
because it definitely maps that way.
It gave examples in here though. It said in an embedding module, embedding of input, embedding where you take the input and you give it a tensor. So embedding of 10.3 padding index.
yeah, we need to get a tensor out of this.
Input equals, so the input has to be a tensor as well.
Oh. Okay.
But you can't really start with the tensor anyway, so
Yeah.
there's got to be another way to do it.
Yeah.
Well, that's okay. I mean, I just wanted to make sure that I understood correctly that you could dig into that architecture and pull out the pieces and do things with it. That's the main thing.
Yeah, it looks like you can. I just don't know how to do it right now. Let's see.
I mean, that's basically what.
You can probably look into it and just make more sense of it. I haven't done it, but I definitely have done it once, but I haven't used these embeddings, formally. So I don't actually remember, but definitely you can do it if you want to, because the embeddings have definitely been used for, let's say, in like a word2vec format. It'll be like a 400 cross embedding, and it's pretty useful to use as embeddings. Generally, because we're not using a BILSTM like Elmo, so they probably might not have as much context like you think an LSTM based embedding model might give you, but they're pretty useful.
And you use them. You use them. You take sentences. You said similarity. Do you like take the words from a sentence and the tensors and like average the tensors, that sort of thing, and then compare the two sentences? Okay.
So it created an embedding object with 60,000 entries and 400. And so each word, there's 60,000 vocabulary words, and each one of them is embedded in a 400 dimensional vector.
Yep.
That's
that makes sense.
But we should be able to give it a word and find out what the vector is. I don't know how to do it.
Or the index of the word. Yeah.
Yeah, or an index. Yeah. Yeah. So I don't know how to do that, but maybe there's a method that you have to use. See, here's all the methods, right? If you see any methods that look like they might work. So in EE, the embedder, the encoder has all of these methods.
Wait a second. EE.data. Can you do EE.data?
EE.data. Okay.
Yeah. Or something. EE.weight.data. EE.weight.
EE.weights. Okay. So let's see.
EE.weight. EE.weight. Yeah.
EE.weight. EE.weight. Let's see what that
so that should give you 60,000 comma 4.
Okay.
So the shape of this should be 60 cross. If you do e.weight.shape, can you just see that?
Yep. Yep. 60,000. So there's our tensor.
So you do e.weight 360. Can you do that?
Yeah. So we go weight. Let's see. One. Insert the cell below. Weight. Let's see. Slices must be integers.
Oh, you just need to do
360. I gave it I put a dot. I didn't mean to put that dot there. I meant to put a comma there. That's what I wanted. There it is. So that's the embedding of less. The word less.
Yeah.
This is what you were after, right, Darren?
Yeah, sort of. I wanted to see how you could interact with it, and there you go. It's nice because the fast AI, you get like this best practice very quickly. You get a neural network architecture, and then as you go along, what's interesting is you can go in and monkey with it and use pieces of it. So
that's the whole thing.
Yeah.
And that's, in order to really learn fast AI, that's really what we have to do to be able to, and whenever you solve a real problem, then you end up having to go in under the hood and finding out what's going on in there. Yeah. Well, I want to thank everybody. This was a great session, and thanks to all the people who had made all these contributions to our discussion. I think it's great, and I'm pretty sure it's recorded, so we'll have it for people that want to tune into it later.
Joseph, you don't save notebooks from that you edit live, do you?
I actually do, and what I will usually do is I'll go over this notebook, which doesn't work right now. I mean, this one I made it work, but now we made these little annotations. I think I'm going to go through and fix it up and then save it again and push it to the repo. Is that what you were asking?
Yeah. Oh, that would be great. Thank you.
Yeah, and I'm going to do the same thing if I ever get this one working, the Vietnamese and the Turkish. I'm really bothered by the fact that they're not working for me. I'm going to make them work and push them to the repo as well.
As into your personal, the personal one, the individual one.
Yes. Yeah. And so I've actually put some of the revised notebooks that I created. I pushed them to. I actually made pull requests onto when I thought I had good notebooks, the ones that I finished. I made a pull request on the FastAI NLP repo, the real repo, and a bunch of my notebooks just got merged into the real repo now. So they liked them, I guess. All right. Well, I guess we're done for the day, and thank you all. People I'll put this chat on. I'll put the link, the chat on the Slack group because people have contributed a lot of good links and so on. So we'll have that.
Thank you.
All right. Yeah. Thanks, everybody. See you next week.
Thank you.